welcome, and we are anxious for your second lecture. So you can start. Everyone on YouTube or Google Meet can make their questions. I will read it on lecture, and maybe you can also make during the lecture an interview.
Sure, you can, yes.
Okay.
The time. Yes.
So good lecture, guys.
Okay. So good morning. Today we're gonna start the studies about detectors. Okay. And then we'll try to use what we learned yesterday and try to understand the basics of the particle detectors, and we will try to apply it for the gaseous detectors. Here are my contents. And then first we start with the particle detectors. And so what is a particle detector? The name is clear. Is some devices that we use to detect particles. Okay, are discussing about many particles yesterday. Now we are going to understand how we can detect it. For example, a gaseous detector. And first we start with the general characteristics of a detector. And the first one is the sensitivity. So what is the sensitivity? Basically, how we can produce a useful signal when a particle passes a detector. Sometimes, for example, we have a detector A. Second, have a detector A, and then with this detector we can detect, for example, electrons, but we cannot detect good kaons. It means that the sensitivity of this detector is good for electrons, but not good for kaons. Or we have, for example, a detector B, and with this detector B we can detect very well gammas, photons, but we cannot detect another type of particles, let's say muons. So this detector B, good detecting gammas. This is sensitivity, and the sensitivity will depends on the particle that we are trying to measure, on the energies, and on the type of the detector. Because depending on the particles and depending on the material, the interactions will be important for electrons, gammas, and so on. And the second characteristic is the detector response. This is basically the ratio of energy that a particle lost inside the detector divided by the signal. Imagine we have a detector like this, and then we have some particles passing through it. Okay, and then it will eventually excite and ionize the detector. Like yesterday we saw they have collisions with the atoms, and then they will lose some energy inside the detector. Okay, they will lose some energy. And then if you take this ratio here on the left, the energies that we lost here, and divided by the signals that we are measuring, we expect this to be linear. Okay, this be linear. Because this is clear, right? Because if we have more energy, we should have more signal. And then we expect this to be linear, because if we increase the energy, we would increase the signal that we are measuring. So this is the detector response. Okay, now another thing here is the resolution of a detector. We can talk about time resolution, we can talk about spatial resolution, and also energy resolution. Basically, the energy resolution is how we can distinguish between two different energies. And this we can frequently give this in function as the full width at half maximum. As you can see on the left plot, we have a Gaussian with the energies distribution. This FWHM is the half of the height of this peak. And then if the energies are closer than this value, we cannot distinguish between them. This is what we do when calculating the energy resolution. Or I can give you a very nice example, which is very easy to understand. Imagine we have a detector with resolution, let's say this 0.1 megaelectronvolts, and then we are taking 3 types of energies. Energy 1, like 1 megaelectronvolt. Energy 2, 1.05 megaelectronvolt. Energy 3, like for example 1.5 megaelectronvolt. So let's do some calculations here. Imagine we have E minus 1. This is 1 minus 1.05. Okay, that takes the module. And this value, this E2 minus E1, or this is the opposite. 0.5 minus 1. Okay, this is lower than R. It means that we cannot measure these two closed energies because the resolution is 0.1 and we are trying to measure 0.05. That's not possible. But if we try to measure E3 and E1, this is 0.5 and 0.5 greater than R. So yes, we can measure this guy. Also, we can measure E3 and E2. We can distinguish between E3 and E2, E3 and E1. But we cannot distinguish between E2 and E1 because they are too close for our detector resolutions. We cannot measure different energies. Okay? So, yes? Sure. Beleza. Valeu. And guys, here it's important that the resolution of a detector, it is varies as this energy to the minus 1.5. And then as we increase the energy, we can see that the resolution is going a little bit down. So this is a very nice thing to understand. When we compare different particle detectors, we can use a detector A for measuring a kind of radiation, or detector B depending on the resolution. So this is a parameter that it's very important for the particle detection. Okay, now we move to the next one. Now the next characteristics is response function. This is basically the distribution of pulse heights that we are measuring from radiation. Okay, imagine we have 2 different detectors. This is the germanium detector, and this one here, like a crystal, the organic scintillator. And then we would like to measure gamma radiation, photons, and with a specific energy. So take a gun of gammas, let's say a cesium, and then we produce a lot of radiation with the same energy. And then we could take the height of the pulses, and we see that the 2 detectors, they are showing different plots. Why? Why is this? Because this is the response function of each detector. Each detector will show a different response function for the radiation. For example, for the germanium, we see this peak here, and also this small distribution here. There are 2 effects going on here. Remember yesterday, we studied the interaction of photons. We saw that they can interact basically by Compton scattering and photoelectric and pair production. In this case, pair production is not being measured here. It's only photo production, photoelectric, which is peak for the germanium detector, and this distribution is due to the Compton scattering. But if we change for organic scintillator, we see that the response is different. It means that here we have more Compton than photoelectric effect. So these are 2 detectors which have 2 different response functions for the same radiation. We can see the difference between these 2 detectors. Okay, now 2 important concepts that are related to the time that we need to form a signal in a detector. The first one is the response time. Okay, response time is the time that we take to form a signal, because every time a radiation passes through a detector, we can see a signal. So the time that we need to form the signal, I will draw here in a little bit, is the response time. The second parameter is the dead time. The dead time is the time to form the signal plus some time that the detector needs to recover from the radiation. Let me draw, and then we can understand it better. hide. So let's say we have a signal like this, and then let's take some points here. Let's define this place as t0, this as 1, and then q1 minus 0 r. Okay, and then let's say if you take after the signal was formed, we have this amount of time we will call t3, and if you take 3, have tt. So tr is the time that we take to form the signal. It's the response, the response of the detector. Okay, and td is the time that the detector is not working because of two things. The first one is that the detector, it needs some times to go back to the ground state, because when a radiation passes the detector, it will ionize the atoms, and then after some time it takes some time to go to the ground stage, and then we have atoms available again. And then we have another issue here, because when we detect a signal, we need some electronics, and these electronics, it takes some time to process the signal and to send to the computers, and there is a dead time related to this. So the dead time, nothing less the time required to form the signal, and the dead time for the detector to recover, and the time for the processing of the signal. So this is what is going on in the detector, and we need to take into account this problematic when designing a particle detector. Sure, you can. I will talk about this later. But if you want, I can explain now. But it's more or less this: we have electric field inside the detector, and then the particle passes through it, and then we create an electron and an ion, okay, a pair. And then this electric field accelerates the electrons. Then we can collect this charge in the wire, and this is the signal. Okay. Red part, yes, the red part, yes. Great. So the last characteristics that I want you to understand is efficiency. So basically, what is efficiency? In simple words, it's the number of detected particles, and that divided by the number of emitted particles. Okay, and then we can split this in two quantities. We can split it in the intrinsic efficiency of the detector and the geometric acceptance of the detector, and then we multiply these two quantities, and then we get the efficiency. Let's go for a draw so we can understand it better. So again, imagine we have a source, let's say again a gamma source, and then we have a particle detector right here. And then we start throwing radiation detector. And eventually we produce a photon that will not pass through the detector, right? Because the detector has a finite size, it's not a whole space. Actually, there is this, and then imagine that we would like to measure the efficiency of our detector. Let's try to measure the components first, okay? Let's measure the intrinsic efficiency, which is given by the number of detected particles over the number of incident particles. This is the intrinsic efficiency of the detector. The number of the n inc are the number of particles that are really arriving at the detector. Because as you can see, we are missing some gammas here because we cannot see because the detector is finite. So let's say that we have that this gamma source is emitting at a certain time 1000 photons, and then we have and detect equals to, let's say, 500. So out of 1000 we detect 500, and then we know that the incident particles are 800. So we can calculate each of that efficiencies that I showed there. Let's do first the N geometry. Sorry. To the geometry. How can we do that? Okay, we take the number of incident particles and divide it by the number of emitted particles. The incident particles are 800 and the emitted particles are 1000. This is 80%. Means that out of 1000 particles that are being produced by the source, we are detecting 8% of it because the rest are going somewhere place. And then the intrinsic efficiency of the detector given by 500 over 1000. And this is, sorry, no, that's not what I want to. Is N detect is 500 over N 800. This is more or less 62%. Means that of the particles that are arriving at the detector, we are measuring around 62%. Okay, and then the total efficiency is given by the product of these two quantity, or we can take the total equals to 500 over 1000 is 50%. Okay, this is our detector, and we can split in two quantities. Okay, a picture. Okay, let's move to the next part. So now we're gonna start the gaseous detector, and then my main goal today, guys, is that you can explain. No, it's not working the simulation. Can I send you another presentation? Because this is the PDF is not going the second. Because I have a presentation that shows a simulation. Thank you. Sorry. But this is important for you to understand this. Yeah. I'm gonna send you your email, okay? Okay. Sent. I always do this when I lead with PDFs and presentations. As you just open the just a second. I will make it free. Okay. Oh, spoiler. Okay. Sorry, guys. Now let's. So, by the end of this lesson, I want you to explain what is going on inside the gaseous detector. So we have more things to explain before you can understand it. Okay. So let's move. First, some history. The gaseous detector we started almost 100 years ago with the Geiger counter. was developed 1928. So in 4 years we will be celebrating this. And from this simple device, we were able to develop another types of detectors. For example, we have two main detectors that are the parallel plate counters and the proportional counters. They are basically the same. What changes is the geometry. And from the parallel plate counter, in 1981, this guy here, he developed the resistive plate chambers, which are detectors that are used at the compact muon solenoid. I work with detector today. My main research is about it. And from the proportional counter, we have also the development of the MPD, these chambers here, for Sharpak as well. Guy here. I will go to talk about a little bit on this detector. And then we have a lot of developments that were that took place in these years. And also today we have some developments that are improving how these detectors works. Okay. Today, for example, we have the gas electron multiplier. And by the way, this is the detector that we are simulating here. And then if we are able to understand this simulation, we are able to understand any type of gaseous detector. So very important for you to understand what's going on, so we can explain in here. So about the Geiger counter, the first prototype that was developed in 1908 was not a gaseous detector because it was filled with air, was not properly because it was only sensitive to alpha particles, not beta and electrons. Then after 20 years, we developed the Geiger-Miller detector, 1928, as I mentioned before. And basically, this detector we use to count particles or to simply detect radiation with high efficiency. We go to visit some radiation area, we need to carry this guy to spot any kind of radiation that is close to us. Okay, and it's very used today in radiation zones. And based on this guy, I will start introducing how this type of detectors works, and this is related to your question. Okay. Okay, take this guy here, this cylinder. If we fill with some gas and then we put a high voltage source, produce an electric field inside this guy, what will happen? We put the positive here on the wire inside the detector, and the negative on the most part of the detector. And then what will happen if ionized particle passes through it? What will happen? It will eventually ionize the atoms, and then it will break in an electron and an ion, as I mentioned before. And then the electron will be accelerated towards the anode, because here is the positive potential. And then we can collect these electrons, and then we can produce signals. This is more or less what is going on here. We can produce a signal when we accelerate the electron due to the electric field that is inside. And then if another particle passes, we have more signal we can collect. And then to understand, let me out to understand. Can you see this plot? Okay, we have some regions that we use to operate our gaseous detectors. Let's try to understand each part of it. This first region, first of all, here we have the charge collected here on the amplifier, and here we have the voltage applied, this voltage here. I mean, if we increase the voltage, we will increase the electric field inside the detector, right? And then if suddenly I start to increase the voltage, what will happen? I will collect more charge. And then this at the beginning is very fast. That's why we see this increase here. But eventually, even if we increase more the voltage, it will now be constant. Why? Because we collected out charge inside the detector. We don't have more charge available. However, after some time, we see again increasing. Why is this? Because at some point, the electrons that were knocked out from the atoms, they have energies that they can themselves ionize all the atoms. So we produce more charge, more charge, more charge. And then this is going like a proportional region. And this is a very nice place because here we can count the number of pairs that are being produced. It's more or less linear, like a response that we saw before, okay, for this type of detectors. And then at some point, the electric field starts to be very, very high, and then we lose the control of the linear properties of the detector, and then we start decreasing like an exponential again. And then this we cannot use it to measure because there is no trend. It's an exponential, we don't have control. But at some point, there is a saturation zone that any particle that passes here, you produce the same signal, even if it's a alpha particle or a beta particle. And this is the main principle behind the Geiger and the Miller counter. They operate at this region. However, guys, after this, if we increase even more the voltage, we will start to create a spark inside the detector, and then we can break the detector, and then we can lose it. So after this region, we cannot play with it anymore, okay? So we have, let's say, 3 regions where we can identify particles. The ionization chamber, the proportional counter, where we can count the number of pairs, and the Geiger, where we can identify any type of radiation, regardless of its type. So this is the main basis of these guys, and also for most of the gaseous detectors. Okay, now about the multi-wire proportional chamber. This was like a revolution inside these technologies, because before this, we could not detect a lot of particles at the same time, because we could break the detectors. But then this guy designed a detector like this, and then we could measure at particle rates of kilohertz with very nice spatial and time resolution, because now we have many places to detect our particles because we have many wires to detect it. Okay, and then due to this invention, he was awarded with 1992 Nobel Prize because of this detector. And by the way, this type of detector is well used today for large experiments that we have at LHC. For example, we have the drift chambers that are the same technology that was proposed by Sharpak. For the next, this is important for today and also for the particle physics. It's important for today because it's related to our simulation. Okay, and then the name of this technology is micro pattern gaseous detector, and is more or less a new technology because it's conceived in 1990s. And the difference here is that we have a very high spatial resolution because we have this foil, and then we make a lot of holes, create the electric fields. And so the distance between the holes is 140 micrometers. That's why the spatial resolution is very nice kind of detectors. And then we can operate at high particle flow. And then an example of this guy is the GENS, the gas electron multipliers, which are the examples that we are treating today. And another thing that is important here is that the electrical field inside this guy is more strong, closer to the holes, as you can see by the lines. We have a particle here, you see that the lines are not too close, and then the electric field is lower. And this is important information to understanding the simulation again. Okay. So let's start with some principles that I already mentioned, but let's see how it goes. First of all, we are going to talk about ionization and excitation. Here these two drawings. Excitation is when a particle passes and then it does not have enough energy to knock out an electron, but it makes our atom to go to a excited stage. That's why you have a X star. The electron achieved some energy, but it was not knocked out from the atom. However, if you have a particle with energy which is higher, eventually it will ionize our particle, and then we can remove the electrons, and then we create the pair electron and ion, right? And then we can calculate this number of electrons and ions, and then we can measure. How do you do this? We just take the number of total energy that was deposited inside the detector, and then we divide it by W. What is W? Is the energy loss for each pair. Means if we have, for example, energy like 1 eV, and for each pair no. That's, for example, for 10 EV, for each pair we lose 1 EV that we created, 10 pairs, because each pair deposits 1 EV. Okay? And this is a statistical process because every particle that passes there has a different energy, and depending on the place that it will passes, it will collide with some particles of the detector, and this is described by statistical process. And remember yesterday that is given by the mean free path that we showed yesterday. And then here we can calculate this guy by taking the atomic mass, the Avogadro number, and two important parameters are the gas density and the cross section. The gas density is important because if the gas is more dense, it means that we have more particles to collide, and then the mean free path will be lower. So we can control our detector by changing a gas for a more dense or less dense based on this. And this is important because we can calculate the efficiency based on this information, as I will show in one slide. And then taking the lambda, we can calculate the number of interactions of a particle. And again, as this is a statistical process, this is the average number. Okay, there are a lot of calculations before we can arrive here. It's a very complicated approach. We don't have time to cover everything, but the number of interactions that we are having inside a gas detector is given by L, the distance that the particle travels, divided by the mean free path, and calculate this. And then we know from the statistics that this distribution is the form of the Poisson distribution, and this is given by this equation. This is the probability of a particle ionizing K atoms. For example, if we want to find the probability of ionizing one atom, we do K equals 1. 2 atoms, K 2, go on. And how can we use this to calculate the intrinsic efficiency of a detector? It's very nice to see this. We do K equals to 0, and then we take 1 minus this. Why? Do you know why? Why? No? Because, oops, sorry. Because when you do K equals to 1, 2, 3, 4, and infinity, this is the probability of a particle ionizing 1, 2, 3, 4, blah, 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 blah. If I take 1 minus P is 0, it means that 0 is the probability of ionizing 0 particles. And then 1 minus this is the probability of ionizing 1, 2, 3, 4, blah, 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 etc. Right? And then this is given by 1 minus this exponential. And then I put 2 examples here for you to calculate. And then I have some one problem that you can play after the class. So, example 1. Imagine we have a particle detector, the lab, and then we have 1 centimeter of argon inside the detector. And then we can think about, how can I calculate the efficiency of it? I just take the lambda, and then how can I take the lambda? I have a table. Always I have a table for many gases, and then I look, this is argon, and then I see here number of primary electrons, and then if I take 1 over this, I calculate lambda. So lambda is 0.04 centimeters, the mean free path for this detector. Then I can calculate the number of mean interactions by taking the length, which is 1 centimeter, and I divide by lambda, and this is 25. Okay, I have everything now. So how can I calculate the efficiency? Take 1 minus exponential of this minus n. And then I have almost 100%. So it is a very nice detector to detect. However, if we are at the lab and then we can I use a smaller detector? Yes, I can. But let's see how the efficiency will change now. Let's say that this smaller detector, 1 millimeter of argon. Then I take the same parameters. Lambda is the same because the number will not change, but the number of interactions will change because the detector is smaller. Then I'll calculate n by using the new L, which is 1 millimeter, and then I calculate now the efficiency as 92%. So I reduce the size of the detector, and I reduce the efficiency. Okay, this is kind of obvious. And then we can calculate several different types of detectors with several gases, sizes, and so on. And then please do the exercise. Okay. So now two concepts that we are also talking about today and will be important for tomorrow are drift and diffusions of electrons and ions. Basically, imagine we have this glass of water with some particles inside. If I let them in the stable movement, they will spread out because due to the random movement of the particles, right? And this is what we call diffusion. And the same thing will happen with the electron. When a particle knocks an electron, the electron has its own movement, right? Because of the thermal velocities. Then electron will diffuse inside the gas. And this is when there is no electric field. Okay, this is the diffusion because it's a random movement, not accelerated movement due to external electric field. And then we can calculate this velocity using statistics again by using this equation. And the main message here is that we compare electrons and ions, which are our main particles here. We see that with this equation, electrons diffuses faster than ions because of the mass. Okay, and this is a very important information again for the simulation. Okay, and again for any gaseous detector. And then this is the main information here is that the electron is faster than the ions. And normally this is given as a function of also temperature, because if you increase the temperature, the diffusion will be faster. Okay, and also there is the diffusion coefficient, which will be related with the velocity and with the mean free path. And then by using this coefficient, we can calculate the spread of the particles inside, for example, a liquid, or in this case of the electron. So this is the first velocity diffusion. Now let's move to the second one. Remember, this is in absence of electric field, no electric field in this case. Now, when you put electric field, what will happen? The electrons and the ions, they will accelerate due to the electric field, and this is called drift velocity. Okay, and this is the equation for calculating the drift velocity, and will depend on the mobility mu. I will explain a little bit about it, the electric field, and the pressure of the gas. And the main message here is that the mobility of the electrons and the ions will depend on the mass. And again, it is inversely proportional to the mass. So again, for the electrons, the drift velocity is faster. Okay, this is a small example that if we have here a ionization, different electrons will move towards on the opposite side for the electric field, because there is a random movement. Each electron will move the drift velocity, but it's random. Okay, the electron black, yellow, red, and this other here. And again, the main message is that the electron will move faster than ions, right? Okay, guys. Now I put also here some properties that are important for designing particle detectors, just to show that the EDX that we treated yesterday is also important for designing gas detectors, as you can see. Because let's say if we want to build a calorimeter, measure energy of an electron, so we try to kill the electron inside the calorimeter because we want to measure the energy. You know how a calorimeter works, right? So a calorimeter is a device that we use to measure particle energy. If we want to measure the particle energy, we want the particle to die inside the calorimeter, because we can measure all points and then we can take the energies. So we take, let's say, a gas detector. How would you choose for build a calorimeter? I would say that we can think about it where the energy lost is higher, so we can reduce the size of the detector. For example, if we compare xenonium guy here with oxygen, we would prefer xenonium because the amount of energy that particle will lose is higher. Okay, so this is a nice comparison to how we can design a calorimeter. Okay, now are you able to explain what's going on here? This yellow thing is an electron. Think about it. I explained two types of velocities: diffusion and drift. No? Okay. Diffusion. Because remember, here the electric field is very weak. And then when there is no electric field, what will happen with the electron? You diffuse. Okay? What's happening here? Then after 3 nanoseconds, what will happen? It starts to drifting here in region, because the electric field is very, very intense here. Remember that figure with a lot of points that I put with lines. In this region, the electric field is very intense. So the electron starts drifting, and then why is happening this? These red points are the ions. Let's move to the next topic so we can understand what's going on. So when we have a very high intense electric field, the electrons themselves can ionize other atoms, and then can ionize other atoms, and then we can produce an avalanche of ionizations. Okay, this is more or less what we are seeing here. We see we arrive with one electron, and here the electric field is very intense, and then it starts producing a lot of ionizations. This is called avalanche. This is more or less what we have there. We are with one electron, and here is the electric field. As we move to the right, the acceleration will increase. Okay, and then at the first atom, there is no excitation, there is no ionization. The second atom, you see, there is a excited atom here. Then after some point, the electric field is so intense that the electron has a lot of energy, and then he can knock out all the electrons out of the atoms, and then the other electrons can knock out, and then we have this process of avalanche. Okay, this is also, we can see here, there is the avalanche of electrons happening inside the particle detectors. Okay, and this is a very important factor because we can calculate the gain of the detector. Again, our electrons are moving to the wires because the wires are positive in this case. Okay, what is happening here? We have this electron, it is moving towards the wire, and as the electric field is more intense when we are going to closer to the wire, it starts to gain more energy, and it starts to ionizing other atoms. And then we have this phenomenon which is like a liquid drop, and then we see this happening inside the particle detector. And then we can calculate the gain of a detector using this equation. What is this gain? This is simply the number of collected pairs in this wire divided by the number of initial pairs. So we have the gain, how much we create inside the detector. This is important because after some limit, we cannot operate the detector, otherwise it will break down as well. So there is a specific value that we must attach in order to not to break the detector. Go the next slide. Simulations. Because with the simulations, also we use Monte Carlo. Simulating this. There are some specific package so we can calculate this number of initial pairs. No. Possible, yes. But how we know that we are right? We calculate the number of initial pairs, we calculate the gain, and then from there we can get the signal form and how we can measure the number of particles. We compare with data, and then we say, this makes sense. This is true. The gain that we calculated is right. Okay. Actually, we have a specific package, which is Garfield G++. Yes. Yes, it is based on info. Okay, and then to calculate the gain, we can again take the mean free path, lambda, and then we define this probability of ionization per unit length by taking 1 over lambda. And then imagine that we have n electrons, and then we can calculate the number of created electrons after the multiplication. Just take this delta n. This was described by Townsend in 1897, a lot of years before. And then we can calculate by solving this differential equation as the n is the initial number of electrons times this exponential. And then if I divided n by n0, I can calculate the gain, because remember, we define the gain as NF over NI. And then the main message of this slide is that we want to keep this gain lower than 10 to 8. Otherwise, if we will operate a detector with a very high gain, we will start to see very large signals, and then eventually it can break down our detector. And also, it can make the detector process of aging more prominent. The detector, let's say, if we want to operate the detector during 20 years, it can break 10 years in the future. So we must control this value. Very important. Because, for example, in LHC, we are operating since 2008. And then we want to operate for many years. And then we must control the number of ionizations. Otherwise, we can break our detectors before we finish the experiment. Okay, the question is about how we can control. Basically, before launching the detectors at LHC, we bring it to the lab, and then we test with many different radiations for different particle rates. And then we can simulate the conditions of LHC, let's say by taking a lot of radiations, and then we know, this detector can achieve 20 years of operations given the radiation of LHC. So we test before it. We simulate and we test to guarantee that it will be working. Yes, we can change the electronics, we can change the material, because, for example, for the electrodes, you can use bakelites, or we can use glass. If we use bakelites, we can operate at high flow. We know this from the previous experience. So, if the particle flow will increase, I would choose bakelite instead of glass, because the detector can handle amount of particles during, I don't know, 10 years, 20 years. Okay, last step so we can understand finally the simulation complete. The detector that we are seeing there is a gas electron multiplier, a GEN, and this GEN is like a MPGG, was invented time ago, and it's composed by this very thin foil and with 50 micrometers, and we have, as you can see, the holes are very tiny that we can do 70 micrometers. That's why the spatial resolution is very nice in this case. And what else? So to create the electric field here, we put 400 volts. As this space is very close, the voltage drop here is very high. That's why we see these lines very intense here. So basically, the place where the avalanche will occur will be here, okay? Because the electric field is so intense that the electrons can itself knock out all the electrons and start the avalanche. And then finally, we have the simulation again. I think you can explain, right? I hope. If not, yes. And look, because they are not faster than electrons, because of the drift velocities and diffusion velocities. Yes, opposite direction. So basically, when ionization takes place, we create an electron here. Then it goes down because of this random movement. Then until it achieves here the multiplication zone, let's say, and then it starts the avalanche. And then we start collecting the electrons there. You see, down there. The ions move up. Then we can measure the particle. And then we have a lot of holes. And then each hole has a place to detect on the electronics. So I know precisely where the particle is passing. So this is more or less what's going on. And if you are able to explain this, you can take any detector of this type. Could be a plate detector that you can explain, because the principle is the same. What you change the geometry. There are holes, there are strips. This is the only difference. Also the gas. We can change the gas, we can change the properties, but the principles are the same, basically. Like this one? No, yes, it's the same pattern for gens. Yeah, the same. We can make a bigger detector. Well, depends on the principle is the same and it repeats the pattern. So this is a gen detector, which is used for detecting muons. In this case, muons. Muons passes there, and then it will ionize an electron and an atom. Then we see the multiplication. So basically, they are used for muons. CMS detector. Basically, today at CMS we use gaseous detector for detecting muons. Here is because there in the calorimeter we have crystals, and the principles are a little bit different. And there we have a larger volume that we kills electrons, because their muons are not killed inside the calorimeter. They passes the calorimeters and then they goes out, and then the only particles that arrive the outermost part, the gaseous detector, are muons. They are not killed by the calorimeter like electrons, like photons. Yes. So modern applications we are discuss a little bit here are mostly large experiments like CMS, Atlas, Alice, and another type which are very similar, not very similar, but similar to gens. The principle are RPCs. The difference here is that instead of having holes, we have this parallel geometry, like a capacitor. Then we have electric field, which is a constant inside. So there is a difference. And also we use another type of gas here. Here in gens we use argon and CO2. In RPCs we use 3 different type of gases. So depending on the gas, the properties will vary because of this. Okay, but the principle again is the same. And also, beyond high energy physics, we can also use particle detectors, gaseous detectors, to put 2 applications, but there are more. For example, I have a friend of mine who is working with this type of medical imaging. We can make some imaging using particle detectors together with other detectors, so we can do also this. And also in borders, so you are going to another country, and then we have some border control. Then instead of stopping all trucks that are passing there, we can put particle detectors in a building, and then we can spot if there are some strange things inside the truck. Then we can stop this guy and see what's going on. So we can also use this a very nice application, gaseous detector. Now it's your turn again. So not now, okay. So the first problem I ask you to is about energy resolution, and I put this gamma ray spectrometer, and then I ask you to explain how this guy works. I didn't explain, but you can search on the internet. This is my goal. I want you to look on the internet how it can works. And I ask you to name 3 applications of this guy in the science. And the C is really about the calculations. I ask you to see the energy resolution of the system in order to distinguish the two different peaks energy, 455 and 490, the calculation of energy resolutions. The second one is basically to explain the zones that I put here and then explain. And if you don't remember, I put the bibliography where we have the books, so you can read the books again and explain how it works. And now this is the most interesting question, and it's again based on the table that we use it for calculating the efficiency. In A, what I ask for you, let's say we have a gaseous detector, okay, for any kind of gas, and the information I give is that we have 1 millimeter of a particle detector. Then I ask, choose 3 gases with the higher efficiency. So we just take that 1 minus this exponential, blah, blah. Then we calculate here for everyone, and then we see which of them have the highest efficiency for 1 millimeter, okay? For you to play and see different gases. So B, after choosing 3 gases, I ask you to calculate the length of a path of a detector, if road or sort, that it would stop a proton of 10 mega electron volts. Calculate by taking the EDX. You can play with the variables here. Anything you can ask me by email. And then C, in the real world, we don't build one detector. We build many, 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 many. For example, we have 1056 RPCs in CMS. And then I ask you, let's say you have to build 100 detectors with this surface area, 10 by 10. And the idea is that those detectors are intended to completely absorb the proton, 10 eV proton. Then among argon, xenonium, and helium, would you choose to keep the highest efficiency and the lowest cost? Because in the real world, we also are taking care of the monies of the project, so we need to sometimes reduce the cost. And a hint, look the prices on the internet, because we normally when we build a gas, we build in a cylinder, then we can look for the prices. So I ask you also to calculate the efficiency and also the prices. So that's all. That's all.
Thank Mapse. Thank you very much. Really nice lecture. We are kind of out of time, so if you any of guys have questions, you can take it later, or you can ask. And the slides are available on a Google Drive link already in the comments of YouTube. We are going to send by your email, so don't feel pressured to take too much notes about slides. Okay?
Yeah, and then you can ask him by email anytime that you want,
Yeah.
please.
And Mapse is going to spend the entire week here, right?
Yeah, I will be here until Friday.
Yeah, nice. So you can knock in his door.
Sure,
It's
anytime.
2009. So
You can call me after midnight as well.
Yeah.
Not a problem.
So, guys, let's thank Mapse again, and thank you very much for your presence here. Okay, just a comment for the people on YouTube. The transmission will end, and another one will start for another lecture. Okay, it's not the same transmission for different lectures. So during the afternoon, we will have Dr. Torres again for the hands-on activities, and we will see you there. Okay, bye.